Okay, today we're going to be taking notes on 4.4 wave behavior, and this is just the first part of two parts for this section. One way that waves behave is that they can reflect, and reflection is when a wave changes direction due to contact with some barrier. The law of reflection states that the angle of incidence, which is located here we have the incident ray that is hitting a barrier and it reflects off at this angle. We call this angle the angle of reflection, and then theta sub I is the angle of incidence. The reflected and incident rays and the normal to the surface all lie on the same plane called the plane of incidence. It may be difficult to see this from most of the drawn diagrams that you will encounter, but if we look at the picture below, you can see what we mean. Here is the plane that the incident ray is traveling in, and the reflected ray is also occurring in this same plane. The normal that is perpendicular to that of the mirror surface in this diagram is also in the same plane. So, as you can see, all the rays that are occurring in this event are all in the same plane or the same surface. Refraction is the bending of a light wave, or it is the light wave that's changing directions as it passes through a different medium. Light travels fastest when in a vacuum, and we know that with electromagnetic waves, they do not need a medium. So in a vacuum, light travels at 3 times 10 to the 8th meters per second. Because light travels fastest in a vacuum, we know that anywhere else that light travels will be slower. So all other media, light will travel slower. The difference in speed is responsible for the phenomenon we call refraction. When light travels from a medium of lower density to a medium of higher density, it slows down. So one thing to note is that when a ray of light strikes an interface between two media, there is both reflection and refraction. So as you can see here, the incident ray that is having some reflection, there is some refraction also. You have a little bit of both. The index of refraction is the speed of light in a vacuum divided by the speed of light in the medium. The n here is the index of refraction, n sub 1, the c equaling the speed of light in a vacuum, and v sub 1 being the speed of light in the given medium. Because the speed of light is always greatest in a vacuum, the index will always be greater than 1. If you plug in some numbers, you do the math, and you can actually see that that comes out to be mathematically correct. Here is a diagram for you to look at. There's a lot of stuff going on, but let's go ahead and just piece this apart. Here we have the surface that separates medium 1 from medium 2. We have a wave front and the rays showing the direction of the wave and the energy heading into the second medium. When the wave front enters the second medium, we see that the speed decreases and that the ray shows to be bending. So here we have the normal, and we show that the ray, the incident ray that goes into the medium, bends towards the normal. And also here when this ray goes in, then it also bends towards the normal that's drawn here in the dotted lines. Because of this bending, the wave fronts of the wave in the second medium changes. If we wanted to figure out the distance the wave traveled from point B, which is right here, to point C, that would be v sub 1 t from the speed equation, which is speed equaling the distance divided by the time. We can compare the distance in the first medium to that of the amount of distance covered in the same amount of time in the second medium, which is right here. This is going to be called v sub 2 t. Notice that our angle of incidence is right here, and this is known as theta 1. And our angle of refraction is this area between the normal and the bend in the ray, and this is theta 2. Using our trigonometry rules, we also know that if this is theta 1, this area over here, this angle is also theta 1. And if this is theta 2, then we also know that this is theta 2. If we use Pythagorean's theorem, we can then make a connection between the angle of incidence with that of the angle of refraction. When solving for the hypotenuse, which is right here, the red line, for both of these triangles, because here we have the angle of incidence and the angle of refraction, we would get that the hypotenuse would equal v sub 1t sine of theta 1, and that's, remember, sine of theta 1 is the opposite over the hypotenuse, and that the hypotenuse here, in order to figure out this area, we would do sine of theta 2, and that would be the opposite over the hypotenuse, and that would give us v sub 2t sine theta 2. Because the hypotenuse is the same, we can then set these two equal to each other. When we do that, we get v sub 1t times sine theta 1 equaling v sub 2t times theta 2. Time cancels out, and we are left with v sub 1 sine theta 1 equaling v sub 2 sine theta 2. We move things around, and we can show that v sub 1 over v sub 2 equals the sine of theta 2 over the sine of theta 1. We define a quantity called the index of refraction for a given medium as n equaling c divided by v sub 1. Likewise, if we were to solve for speed here, we'd have speed equaling the speed of light divided by the index of refraction for a given medium. Substituting v into this equation, knowing that we also have v sub 2 equaling c divided by the index of refraction, we plug this in here and we get c divided by n sub 1, all multiplying sine of theta, equaling c divided by the index of refraction for the second medium times that of sine of theta 2. The c's cancel, and we are left with n sub 1 sine theta 1 equaling n sub 2 sine theta 2. This is Snell's law. If we then rearrange things, we get n sub 2 divided by n sub 1 equaling sine of theta 1 divided by sine of theta 2. Or you can also state it as this, which is showing 1 n sub 2 equaling sine of theta 1 divided by sine of theta 2. And this is just stating that the ray is going from medium 1 to medium 2. Now, Snell's law, we mentioned, in your packet, you're going to see them place all of these equations together. So it's showing that they're all related in some way. And in my last slide, I showed you how they got parts of that. They're just sticking it all together. And so we have Snell's law being n sub 1 divided by n sub 2 equaling sine theta 2 divided by sine theta 1 equaling v sub 1 divided by v sub 2. So they took three different equations and plugged them all together because they pretty much just equal each other. Snell's law is this equation, and it pretty much just states the relationship between the speed of the wave in the two different media and the angles of their incidence and refractions. It is the ratio of the sine of the angles of incidence and refraction of a wave that is constant when it passes between two given media. Here's an example. A ray of light travels through the air with an index of refraction of 1.00 and approaches the boundary with water, of which has an index of refraction of 1.33. The angle of incidence is 45.0 degrees. Determine the angle of refraction. Go ahead and try this on your own and then start the video back up. Here we're using Snell's law. And so we're using n sub 1 sine of theta 1 equaling n sub 2 sine of theta 2. We are trying to find the angle of refraction, which is theta 2. So what we do is we move everything else over, we plug everything in for what we know, and when we do that, we get an answer. Here we have our n sub 1 for our index of refraction, 1.33 for the index of refraction for medium 2. We have sine of 45 degrees, which is the angle of incidence. And when we solve for theta 2, we get an answer of 32.117 degrees, which is 32.1 degrees when you take significant figures into account. Some things to know is that light bends towards the normal when it enters a region of slower travel. Let's take a look at this diagram over here. We have an incident ray that is traveling in the air, and when it reaches glass, it refracts, and as you can see, the trajectory is a little bit more towards the normal, which means that it's traveling into an area of slower travel. As we go through the glass and the incident ray comes back out into the air, you notice that the ray moves outward from the normal. So light bends away from the normal when it enters a region of faster travel. Another thing to note is that the wavelength changes, the speed changes, but the frequency stays the same. And this is denoted by the wave speed equation C equaling lambda f. Remember that the number of waves that enter a medium equals the number of waves that exit in 1 second. Thus, the time factor, the frequency, must be constant. If frequency cannot change, then the only other thing that can alter is the wavelength. Because speed is changing, lambda has to change because frequency is staying the same. So when do we see refraction at work? When you are looking at a pencil at an angle in a container of water as seen here in this diagram, the light waves that are coming up from X bend away from the normal, and the normal would be perpendicular to that of the surface of the water. And so the ray of refraction would be pointing away from the normal because the ray of light enters into a medium that is faster. This makes the pencil seem to originate at point Y. This picture is not to scale, but from any angle of view, Y should be vertically above X, and the pencil should appear to be shorter, not longer as seen here. Here is what it would really look like. So you can see that it looks like it's above. So this part right here that we're seeing is this part in the diagram, and it does look shorter and it looks closer. Let's say we have an incident ray going through this medium here that has a rounded side and a flat side over here on the right. If you notice, this dotted line is the normal, and this is the incident ray with the angle of incidence, and the angle of refraction is right here. We also do have a little bit of reflection. As the ray enters into the air, the speed of the ray increases and the ray bends away from the normal. If we move the direction of the incident ray a little bit more down to this direction, down to the right, then the reflected ray would change to move further from the normal. It would move closer towards this surface. Then the reflected ray would change to move further from the normal. If we again move the direction of the incident ray more to the right, down here, then the angle of incidence gets larger and the refracted ray moves even further from the normal. If we move the incident ray more, we would eventually get to a point where the angle of refraction would be 90 degrees to the normal as seen here. At this point, the angle of incidence is said to be the critical angle. Here is the angle of incidence, and we call this the critical angle. Let's go ahead and write that in TNOTES. So critical angle is when the angle of refraction is 90 degrees to the normal. Here we have a light source in the water that is pointed at different directions, different angles. When the angle of incidence is within the critical angle, then what we experience is that the angle is refracted. When the angle is at the critical angle, it is refracted at 90 degrees. And beyond the critical angle, we have internal reflection, and that just means when the incident ray reflects back into the same medium that it was traveling in. Here's a picture of a person who is looking into the water and seeing the image of a fish. Now, from the surface of the water, it looks like the fish is here. However, the real fish is deeper in the water due to refraction. The light comes from the water, and it enters into the air, and because it is entering into a medium that it can travel faster, it is bending away from the normal, and it goes into our eyes, and we follow this red line, and you can see this dotted line right here, and this is actually where we think the fish is, but we are only just seeing the image of the fish. So here we have a picture, and there's a fish in the water that is looking up. This could be the perspective of a fish or anything, like even a person who is diving underwater, and this is what they would experience. Because of refraction, what the fish or the diver would see, it will always be off by some amount. In this case, the fish thinks the position of the bird is here. However, the actual bird is further to the right, and that is because the light that's coming off of the bird into the water gets bent, and it actually bends towards the normal, which means it's slowing down. And what you'll notice also is that the scope of view is squeezed into a cone of an angle of about 98 degrees, which is twice that of the critical angle because we have half of it over here and half of it over here. Everything outside of this scope right here on the left and in the right area is going to look very dark to the person that is looking up. Here's a real life example. It's a little cut off, but if you can imagine that this is a circle, and we have here someone who is looking down from below within the water. Everything inside the circle is refracted light from the surface of the water. Everything outside of the circle is a reflection from the bottom of the water that the person is taking the photo from. It is dark in this outer region because there's no light that is reaching that area. Therefore, we see darkness in the photo that is outside the circle. Here's an example. Go ahead and try this and then start the video back up. So the question is, will the incident light ray reflect or refract, and at what angle? Here we have an incident ray that is traveling in a medium which has an index of refraction of 3.4. The ray would then travel out into the second medium, which has an index of refraction of 2.6. Here is the angle of refraction, and the 28 degrees is the angle of incidence. The first step that we would want to do is find the critical angle. As we know, the index of refraction decreases as we go from the first medium to the second medium. Because of this, the speed is going to increase, and we know that the ray is going to refract away from the normal. The first step is to find the critical angle. We are given 28 degrees as the angle of incidence. From this, we know that if the 28 degrees is greater than the critical angle, then the ray will be reflected at 28 degrees. If the 28 degrees is smaller than the critical angle, then we know that the light will be refracted. After knowing this, we know how to solve the problem. Let's use Snell's law to find the critical angle. Let's also call theta sub c for the critical angle. It could also just be theta 1. Given our Snell's law, here we have n sub 1 sine theta 1 equaling n sub 2 sine theta 2. Let's plug in all of our information that we know, and what we do know is that the angle of refraction, in order to be a critical angle, has to be 90 degrees. So we're going to just put 90 degrees in here for theta 2. All the other information is from the index of refraction of the first medium and the index of refraction for the second medium. When we solve for theta 1, we get an answer of 49.88 degrees or 50 degrees. Because 28 degrees is less than 50, we know that the ray will be refracted. Okay, so now that we know the critical angle, we also know the angle of incidence, and we know the index of refractions for both of the media, we are going to now find the angle of refraction. We use Snell's law, and we are solving for theta 2, which would be the angle of refraction here. And when we plug everything in and we solve for theta 2, we get an answer of 37.87 degrees or 38 degrees. Now, how do we use refraction? Let's go ahead and take a look. Right-angled prisms are very useful in today's world. If we put this prism at this angle. We put some light going into it at an angle that is perpendicular to the part of the surface outside, and it hits in the center here. Which direction would the ray reflect? It would go in this direction. And what we notice here is if it was a critical angle, then the angle of refraction would actually be following along this part right here, which would be perpendicular to that of the normal. But because the angle is actually bigger than that of the critical angle, we know that the ray would actually shoot this way. Now, some examples of what we call total internal reflection, and that just means all the light gets reflected back into the medium in which it was traveling. You can see it here. We also have it here where you have a laser that's pointing through and it travels through, and actually it's even going internal reflection at these points. In the center here, you'll see a diagram that shows the entire setup where the person would place each of his or her eyes, and it would go through multiple prisms in order to eventually reach your eyes. Here's another example of total internal reflection. So there's a reason why we're able to see pictures on top of the water from an object that is below. Another example of total internal reflection is fiber optics. Here we have where the light is traveling at certain angles, and then we see this over here. This same setup is the reason why we are able to have endoscopes, so we can have certain kind of checkups done. So as you can see, very enjoyable. All right, so that's the end of our TNOTES. Please look at some extra information in your Cognity Online, do the review questions, look at the textbook, look at the NOS sections, look at the worked examples, and be ready to use this information in class.